Okay, so today our topic is going to be detailed designs for engineered adsorbent systems and wastewater odor control. So just kind of with that, go ahead and get started. We'll jump right into the presentation. So here is our table of contents. So it's quite a few, or our agenda for today. So it's quite a few topics that that I'll touch on. So I wanted to mention that if there's any questions, please feel free to write them down in the chat or the Q&A, and I will make sure to answer them after the webinar. So that way we can move through the content efficiently, but also I want to make sure that I kind of explain and relay information as clear as possible. So a little introduction, PureAir filtration. As I mentioned, I've been here 13 years, but PureAir has been in business since 2004. So started off very humble beginnings with the owner, Kevin Jameson, as well as maybe an employee or two in his home office. Now, I've definitely watched the company grow. So we have over 30 employees, and we have sales representatives and agents in countries all over the world. Some notable customers that we work with Dannon, Intel, the National Archives, different military, basically different military branches. So really our footprint expands quite a bit with our systems. So PureAir filtration, if you guys are familiar with our webinar series, have you seen this slide before, where we have our main four, I would say, kind of four industries that we focus on, where odor control and environmental emission control, which will be our topic, our main focus today. We also work in different areas as well, as far as indoor air quality. We'll provide systems to purify the air in buildings, whether it's hotels, museums, or removing different smells from kitchen exhaust. Really nice broad range of different technologies for that and different applications. Emergency gas scrubbers. So typically at water plants, if they're using some type of toxic gas to disinfect the water, it's important and required to provide some type of scrubber in place if they're in the event that there's some type of accidental release. So provide those scrubbers to help protect any loss of life or equipment. And also protecting critical electronics from corrosion. So those same odorous gases are very corrosive. So it's important to provide systems to keep those control rooms clean, especially in whether it's a refinery or even a pulp and paper mill. You want to keep those corrosive gases away from the expensive and critical electronic equipment. Not mentioned here, but that's two more industries that PureAir is starting to venture into. One being the biogas industry. We're really doing more research into that area and finding that a lot of our products and technologies can provide some useful benefits for that. And another industry as well is antiviral. So of course, with COVID kind of taking over the news in our minds these days, and it's important that we can provide some systems and some technology to help combat that, at least provide clean spaces or clean environments for different areas, whether it's an office, home. So we're looking into expanding into a few more applications to really increase that PureAir footprint. So thought I'd just mention that. Okay. So for this particular webinar, so I want to talk about some odor control considerations as we dig into designing odor control systems. So it's important to keep in mind that each odor control application is unique. So even though the systems may be similar, you have to take each application and look at the process itself to see what will be the best fit for that. So that's very important. So today we're going to talk mainly about H2S and removing H2S gas, but it's important to uh, look at the total odors that will be present in that application, because it's very important. You can design a system to remove H2S, but if there's those other odors that are present, whether it's the neighbors or the personnel, you're still going to have those odors. So they're going to look at the entire system and say, well, maybe the unit's not working, even though you are removing H2S. So it's very important that we look at all the odors. But for this webinar, we're just going to talk about H2S when we're sizing these different systems. And also, it's important to have some flexibility, because especially for new projects, you may not have all the information up front. So having that flexibility will allow us to kind of customize that system, so that way we can make sure even in the future we have that that flexibility to change up the unit if necessary. So types of sewage odors, again, hydrogen sulfide is our primary focus today, and I would say the most common gas that is required to remove. But there also, you have the mercaptans, some reduced sulfur compounds, such as dimethyl disulfide, dimethyl sulfide, and carbonyl sulfide, as well as ammonia, amines, and some VOCs. So it's important to knowing that process, and get a better feel for what other odors may be present. Here's a kind of an odor threshold, odor detection chart to give you an idea of the different odor and what that smell kind of correlates to. So hydrogen sulfide, rotten eggs, which most are common with. Mercaptans has that more of a kind of a rotten vegetable or cabbage or garlic smell. And some of the dimethyl sulfides and carbonyl sulfides, have different odors as well. It's important to know that the odor thresholds, for example, for hydrogen sulfide is very low, so at 3 ppb, so it's very easily detected. So that's why it's very important. So even if their H2S levels are very low, you still can have those customer complaints in the surrounding area. So that's why it's important to have some type of system in place that can give you that 99.5% H2S removal, or even 99.9%. So that way you really get it below that odor threshold. So the technologies for the different H2S levels. So this is important for us. Really, it gives us that ability to design a system properly, looking at a few different variables, whether it's we want to make the system as cost effective as possible, but also make sure the unit's going to last, or the media is going to have a long life, at least 1 year minimum of life. Because no customer would really be interested in changing out media frequently. So on this particular slide, we talked about, so let me get my, it's all right. So different odor levels, for example, so if you have a very low or intermittent H2S levels, standard adsorbents would work pretty well as far as like a plain carbon. As long as you design that system with a few accessories that I'll talk about later, but that can be used to provide that necessary odor control. Or even in some cases, we can even use our side access housings for these systems. And they are very advantageous because of you can reduce that footprint while still providing a system that will give you high efficiency. H2S levels in the 1 to 20 ppm range. In those cases, you would need a high capacity carbon or an engineered carbon to remove the H2S levels down to acceptable levels. And those particular carbons are more like a H2S sponge. So it is specifically looking for H2S to remove at very high efficiencies and removal capacities. So once you're in the 20 to 50 ppm range for H2S, in that case, it makes sense to use what we call scavengers. And I'll talk about this different scavengers that we use a little later in the presentation. But it was scavengers in combination with the high capacity carbons. Because scavengers they're very efficient at removing high levels of H2S and at a very economical price point compared to the high capacity carbon. So using those in combination, it helps prolong the life of the high capacity media. And then odor levels 50 ppm or above, that's when we would look at using the BEAST biological systems for that. And actually, for this webinar, we will not be discussing the BEAST. That will be in December's webinar. So you guys can stay tuned for that one, for that invitation. So this is the odor, odor control, like a system selection chart. Actually, this chart was used in a previous webinar, but I thought it was very, very helpful as far as what systems you would use based on the airflow as well as the H2S levels. So as you see, if you have very low airflow and very low H2S levels, in some cases, you can use the different engineered adsorbents, activated or plain activated carbons. As that airflow increases and the H2S levels increase, you're fixed into what type of system will be best to use. I also wanted to mention that even the 50 ppm H2S levels, typically we would go with some type of a biological system. Actually, in some cases, if the airflow is low enough, it may make sense to use an engineered adsorbent. So that's something we keep in mind as we're moving forward to looking at the entire design and see what makes sense. So again, as I mentioned previously, all these systems units are for the most part custom. Each application has its own, I would say, its own identity. So you look at all different solutions to a new project. So as I mentioned, for very low intermittent H2S levels, in those cases, it may make sense to use a side access housing. And the benefit of a side access housing, this particular unit here shown in a painted steel, but you can provide a unit you have higher velocities through the media itself. And I'll talk about velocities a little bit later in the presentation, but that allows you to provide a smaller footprint for the system. So now that helps with the cost as well as installation. So it's only recommended for very low H2S levels. Otherwise, you'll be replacing the media quite frequently. But the levels are low. It definitely is a great option. These units are now manufactured out of fiberglass, so that gives it the highest corrosion resistance. And we have a few systems installed in various locations out of fiberglass. And so those side access systems, they are actually equipped with, these are modules, that basically plastic or disposable modules that are filled with the different adsorbent medias to remove the different odorous gases. So typically for wastewater application, we would use we call our PP12 module that holds more of the adsorbent media. So we'll slide those modules into the system and turn that unit on, and it will connect up to the existing duct and neutralizes the air. As I mentioned, very, very effective system for lower H2S levels, as well as we can really reduce that footprint to make the system more cost effective. So H2S levels from the 1 to 20 ppm range. In those situations, you would use a high capacity carbon or engineered carbon. For example, our Sulfazorb XL media. Now, I didn't show a unit for this particular slide because that media, our Sulfazorb XL, can really fit into any one of our units. So really just depends on the airflow that's required, as well as the H2S levels, and then from there we will size the system. So just kind of wanted to mention the high capacity carbon, what we would use for the 1 to 20 ppm range. 20 to 50 ppm, we would use, of course, our self-absorbed XL as a high capacity carbon, but we would actually also use the scavenger that I mentioned previously, which is our self-absorbed FE. So that's going to act as as I call it, a punching bag for the H2S. It's going to take the heavy blow, and then from there, the self-absorbed XL will polish the remaining H2S. Again, this media can be loaded in any one of our systems. So whether the deep bed systems, typically the deep bed systems, media can be placed in the side access housings, but in most cases it wouldn't be necessary. And again, 50 ppm or above, you're looking at the biological technology, and like again, that won't be discussed in this webinar, but we'll discuss it in next month's webinar. But again, as I will mention again, depending on the airflow, we may not rule out a engineered adsorbent system even with the higher ppms. It's just again, it's a case by case that we'll take a look at it. So types of adsorbents, activated carbon, just a plain carbon, whether it's coconut shell or some coal-based, or in some cases wood-based. It is good for general odor capture, especially VOCs. It's been around for quite a while, and it's very effective that way. It's not really designed for H2S, so it's not really hadn't have much capacity for H2S removal. And it's also, there's no way to measure the remaining life of the carbon itself. Engineered adsorbents, we say using either chemisorption principles for the different medias, where you have that particular, whether it's an activated carbon, and it may be impregnated with or combined with a catalyst. So that really lets you focus on particular gases with that media itself. And that media life can be measured as you're measuring the remaining amount of that catalyst. And the scavengers, low cost media, like a roughing media is a better way of putting it for the H2S. So how does gas phase, the gas absorption work? We've touched on this in previous webinars, so I won't dig too deep into it, but I will explain a little, is that the different medias that are used for odor removal are very porous. So that's what's capturing the gaseous molecules and holding them in place. So for plain carbon, it's just as those molecules come in, they're held in place by the media itself, inside the media. Now the problem with plain carbon, as larger molecules come through, it can dislodge the molecules that are in there. So you have they call it desorbing, or off-gassing. So there's that potential for off-gassing in some of the plain carbons. With the chemisorbent medias, since they have that catalyst inside of the media, once those gases come in, they react with the media and the catalyst. So it keeps it inside, so that way there's no way for it to desorb. So once that media is used up, since that is a permanent reaction, you have to dispose of the media and replace it. Here, this slide just kind of touches on adsorption and chemisorption. Won't spend too much time on this slide here, as this has been in previous webinars, but the best analogy for the different medias would be, view them as a sponge. So as a sponge soaks up water and holds the water in place, the same with adsorbent medias, where those gases are in essence sucked into the media itself. So depending on whether you have some type of catalyst will determine whether it's chemisorption or the adsorption. Still a form of adsorption. Here's a microscopic view of this is activated carbon, just to show how very porous that it is. those molecules are trapped inside of those pores. So types of filtration media, you have a physical process adsorption, as I mentioned, activated carbon's example, where it holds the media in place. That process is reversible. So if you've heard of regenerating carbon, whether it's via heat or water, in essence, you're just either washing out or burning out the gases that were trapped inside, and then you can reuse that carbon. The chemical process, or chemisorption, examples of permanganate-based medias, or medias with has a permanganate, impregnated with a permanganate, that's some type of permanganate, is also impregnated carbons. That process is irreversible. So once the gas reacts with that particular catalyst, it turns the entire media itself into like a solid byproduct. So what is activated carbon? In essence, it's just charcoal that's been activated, typically with steam, to open up the pores, to ensure that media, that carbon, will hold on to the different molecules. It's great for removing VOCs, not a great capacity for H2S, and you can have that off-gassing, as I mentioned previously. And again, there's really no reliable method to check and see if it's when it's used up. So in essence, it's more of you have that, I wouldn't say it's a guessing game, but in essence, you're waiting for a breakthrough to determine when it's time to change the media, which is not ideal. So carbon regeneration, as I mentioned previously, two different types of regeneration, whether you're using a kiln to burn away the different adsorbed gases, and then you take that regenerated or reactivated carbon and then reuse it in the system. But at each time that the carbon is reactivated, you're losing that effectiveness. So, over time, you have no benefit of the carbon. And also water regeneration, in situ water regeneration, where in that case, the entire vessel is filled up with water to rinse out the different gases, say for example H2S, and it washes out that, and it basically turns into that sulfuric acid. Well, the problem with the water regeneration is that it doesn't wash out the other odors that are going to be present in this application. So you're going to lose that effectiveness and that efficiency for the media, as well as once you regenerate that system, you have to wait for that unit to dry before you can activate it. So there's quite a bit of downtime when using the water regeneration, and generally we're just seeing that technology phased out. The majority of engineers that we work with and consultants, they're not using this technology at all. So chemisorption, as I mentioned previously, when you have a media that's impregnated with some type of catalyst, for example, potassium permanganate, which will oxidize most odors, and in essence, you're just converting that gas into some type of inert solid that can be landfill disposed, and it's non-toxic or non-hazardous. So different engineered adsorbent medias. So really, depending on what gases are present, will determine what media that we will use to ensure we get that total odor removal. As I mentioned in this presentation, we are discussing H2S, so that'd be our Sulfazorb XL. But again, as we are, as it's very common, there are always other odors present. So when the systems are designed, we ensure that we have the ability to provide some type of, as we call them, polishing medias, to ensure we're going to take out all the odors. So I'll discuss a little bit later kind of our thought processes when designing these systems to make sure we provide a unit that's going to take out H2S for the length of the unit, the length of the desired media life by the end user, as well as to ensure we're going to take out those other odors. Some of the substrates of the engineered adsorbents that are used, whether it's activated carbon used as a substrate, may be impregnated with some type of acid to remove different gases. Aluminas, very popular, as well as some zeolites and the clays. So the clays will be more of the scavengers that are used for like the H2S roughing media. And some of the different impregnates, where there's caustic acids, was oxidizers, and different catalysts. So this slide is really a representation of our Sulfazorb XL. So it is a carbon-based media, but it's actually I'm gonna say impregnated, but they take a carbon powder and they add a catalyst to it, which is typically magnesium oxide, I believe. And so now, and they extrude that into a pellet. So now this media is really great for H2S removal. So it's in essence like an H2S sponge, and it's really looking to remove the different H2S. Now, depending on the what substrate was used as far as the carbon, it may have some capacity for VOC removal, but typically it's designed for H2S. And it has a 66% by weight of H2S removal. So now we can really reduce the size of the system and still provide great efficiency. So as the H2S comes in essence, it is, I don't have this in the way. It is, in essence, that chemical reaction where it separates the water, and then you have a sulfur byproduct. So this media, is landfill friendly and can be disposed. We just recommend that you follow any local codes when disposing. So permanganate impregnated medias, again, that is typically activated alumina that is used, very porous substrate, and it's impregnated with the KMnO4. And we can provide different, I would say different concentration levels of the KMnO4, depending on the application, typically whether it's 8% or 12% to give us that, that added odor removal. How it works is that, so basically that permanganate is going to oxidize the different gases as they pass through the pellet. So in that way, we're going to neutralize a lot of the organic odors. The media is it's non-combustible, so the alumina won't catch on fire or burn, which is very important, typically or mainly in, I would say, toxic scrubbers, where you're dealing with very high levels of a toxic gas, and you have that volatile reaction. So it's important to have some type of media that won't combust. And you also have an added benefit of a permanganate-based media that it changes colors. So as the media is being used up, it starts off a very bright purple, and then from there it goes to more of a brown color, and then it's actually white when it's used up. So that helps give that ability to know, okay, if the media is used up or not. And here, this is a blended media that's, I would say that this is our PureAir filtration's kind of go-to polishing media that we would use, because we're blending a plain carbon and a permanganate-based media. So now we're going to have nice broad spectrum odor removal. So we will place that media, as the last layer in any of our odor control systems. So that way we'll start off with the media to remove H2S. And then after we remove the H2S, we'll go into the second chamber as this polishing media to remove all the other odors. So just a little secret with PureAir filtration, usually if we get requests, different projects will come up and we're given the airflow H2S levels. We'll always design a system to make sure, we have the unit, the media will last a certain amount of time, whether it's a year or 2 years, but we're always going to design a unit to to make sure we can accommodate a polishing media. So that way we can remove those odors, or at least have that ability to do that, provide this media in the future. So I think that's very important to just vividly remember. Is a project where we worked on where they wanted to remove H2S and designed a system for that, and it was no problem. But come to realize there was no H2S in the process. It was other odors, and they had a neighbor pretty close that was still complaining about odors. So in the engineers and the end user's mind, well, this system doesn't work. But actually the system would was designed to remove H2S, and it would do that, but there was other gases. So we were able to provide some different, the unit was designed to accommodate a polishing media, which worked out well. In the Scavenger, again, it's our self-absorbed Fe. So it is basically a clay-based substrate, and it says with iron oxide. So it's going to very efficient at removing high levels of H2S. Again, as mentioned, more of a roughing filter, roughing media. So if you have, there's a punching bag, so if you have high levels of H2S, we can knock that down to about 90% or so, and then from there, make it a little more manageable to remove the remaining amount using a high capacity carbon and also the polishing media. The benefits of the Scavenger, even at very high levels, you may have to replace the media a little more frequently than a high capacity, but it's very low cost. So it takes the sting out of replacing that media a little bit because of the lower cost, the lower price point for this particular media. So different materials in construction for odor control vessels and systems, with fiberglass being the most popular and most recommended, at least by us, as far as any wastewater application. It has the highest corrosion resistance, and it's and also you have a lot of flexibility as far as different configurations for fiberglass with different molds, and we can configure it and customize it to fit in most footprints and spaces. High density polyethylene, in some cases very very popular, starting to gain more, I would say, more traction as far as the material of construction. You have a little more improved cost than fiberglass, and also you have improved long-term UV protection. In some cases, really just it may be the consultant's preference whether they want fiberglass or the HDPE. Either material construction is acceptable to PureAir, so we have that flexibility that way. 316 stainless steel, very common as far as the metal itself in wastewater applications. In regards to for odor control systems, it's definitely effective, but it's very important to make sure that the system's designed properly. And what I mean by that is you need to have some type of mist filter on the inlet of the system itself, because you don't want to have that let's say that potential as you have a wet, moisture laden air combining with the hydrogen sulfide, creating sulfuric acid in the system. Over time, it could start to corrode that even 316 stainless steel. So very important. So it's okay to use 316 stainless in lower odor applications. In my recommendation, but if used in even mid-range H2S levels, it's definitely important to ensure that there's some type of mist filtration on the inlet of the unit. So some different, again, materials construction. Fiberglass, it shows these particular systems are horizontal. Kind of gives you an idea of the flexibility of molding that fiberglass to fit in very, very tight spaces. So very popular in regards to lower profile systems. And you still have that and that excellent corrosion resistance. High density polyethylene, typically you can fabricate the units more rectangular styles, but typically you'll see those in more of a cylindrical design. In this particular unit, where it has the sample ports for sampling the media. You have the blower section, as well as some type of mist filter before on the inlet of the system to capture any moisture before it goes out. It goes into the media section itself. And also 316 stainless steel. Again, as I mentioned, higher for these configurations of systems, the horizontal, and I'll discuss that a little bit later. 316 stainless steel was very popular, as you can bring in different sheets of metal and then weld them together. Now, fiberglass will be the material of construction of choice in almost all applications, as our recommendation. But different depending on the odor level, 316 stainless steel is an option. All right, so different configurations. So vertical flow versus horizontal flow, upflow versus downflow, and then blow through versus draw through. So vertical flow systems, very common, very popular, really for different different applications. Really depends on the space. Any footprint restrictions or space restrictions will kind of determine which configuration may work best for the consultants or end users. Very simple constructions for really all of the adsorbent systems. We have the inlet mist and grease filter, very important. We want to keep that adsorbent media dry, because you don't want any water molecules or droplets, I would say, blocking up the pores, which or any grease to block up the pores, which will limit the effectiveness of the system. I have the blower and the vessel, then the adsorbent media. Horizontal flow systems, really the same design. You have the blower, vessel, the media, mist and grease filters, but now all the components are in a, I would say, more streamlined, or so they're all connected in one complete unit that can be dropped into place, ducted in, and then powered and run. So from our experience, our recommendation typically would be for horizontal flow systems. As I mentioned at the beginning of the webinar, with PureAir filtration, we ship systems all over the world. So it is much easier to ship the horizontal units, as they are designed to fit in ocean containers. So it makes it a very compact, low profile system that can be used worldwide. So it also gives flexibility as far as the different media, separate media chambers that are used to provide, so we can provide different adsorbent media depending on the different gases. So as I mentioned, as we design systems to remove, say, H2S, but we want to make sure we allow or account for other odors that more likely will be present, we can have those independent chambers that allows us to have that flexibility in the future. So upflow versus downflow. Typically this will, I would say the majority, and this is really in reference to more vertical systems, upflow versus downflow. I would say typically on odor control units, 99% of the time it will be an upflow design. So you have the blower itself that blows into the bottom of, say, using the drum as an example in the photo on the left side. So as the odorous air comes in through the blower, blows into the bottom of the drum, and then that odorous air moves its way through the adsorbent media and then is discharged out through the stack. I would say the most common design for odor control. The draw through design, typically seen in toxic gas scrubbers. So it allows you to remove the, if only a certain amount of the media is used up, you can just remove, kind of skim off the top that media that's used and replace that only. So typically with a upflow, it's very important to have a mist and grease filter. So and that will ensure that there's no, mainly grease, that will get into the bottom of the unit, and that'll plug up the perforated screen. So as long as there's a mist and grease in place, the upflow design for these vertical systems is probably the best design to go with. Blow through versus draw through. Again, for vertical systems, I would say about 99% of the vertical systems will be odor control systems will be blow through. So you'll have that blower on the basically on the dirty air side with the mist and grease filter. It's going to capture. It's going to, in essence, you're bringing that air through the blower and blowing into the vessel with the adsorbent media. With the typically horizontal systems, they can also be designed blow through, but our preference is draw through design for a couple reasons, or a few reasons. One, we're ensuring that the blower is on the clean air side of the scrubber itself. So that gives us flexibility on the different materials of construction for the blower itself. So you just have that flexibility. I'll talk about the different materials of construction for blowers here shortly. And also it allows, depending on the design of the system, when you have the unit under vacuum, or the vessels under vacuum, the way the maintenance act or any access doors are designed with the gasket, instead of pressurizing that vessel, you're actually putting the vacuum, so it helps it a better seal. So, our preference is always a draw through when we're working with any type of horizontal system. But again, we could do a blow through, but for those reasons, we would go with the draw through. As I mentioned, materials of construction for the blower. So we got fiberglass, reinforced plastic, which is most common, stainless steel, cast aluminum, polyethylene. So again, fiberglass, reinforced plastic, I don't really need to spend a lot of time on this material of construction, as it's the most common. You're going to have the highest, really the highest corrosion resistance, and also probably as well as strength when designing the systems themselves. Go very high airflows with these units, and high pressures as well. So very tried and true blower, fiberglass blowers for really all wastewater applications. So stainless steel and cast aluminum, I put them on the same slide because they would really fall in the same category. I would only use a stainless steel or a cast aluminum blower in low odor applications, or in a draw through design, because I want to keep those blowers on the clean air side. Typically, the 304 or 316 stainless steel blower, it will hold up generally well to H2S, but really wouldn't trust it under high levels of H2S. Same with cast aluminum. Typically, those blowers are coated. They're cast aluminum, so they hold up well to H2S, but they'll also be coated to provide that extra corrosion resistance. So very effective and very cost effective using stainless steel or cast aluminum in wastewater applications, as their price point's much lower than a fiberglass blower, but definitely recommended to put those blowers on the clean air side in a draw through configuration. And polyethylene, again, very great corrosion resistance. It's probably just as high as fiberglass as far as the corrosion resistance, holds up pretty well. But as far as the actual strength of the blower itself, it may be best to use a polyethylene blower for some of the lower airflows. So if you're somewhere 1,000 CFM or so, or a little bit lower, in some cases the polyethylene blowers make a lot of sense, as it gives you a great price point, but as well as has a higher corrosion resistance compared to a stainless steel or a cast aluminum blower. So again, it just matters, as you take a look at each application, see what blower makes the most sense. Because from our experience, it doesn't matter how low the airflow is for FRP blower, it usually stops at a certain price where even if it's 100 CFM, it's the same price as a 500 CFM blower. So, some of the items that we take a look at. So some of the accessories, as I mentioned previously, mist and grease eliminators or pre-filter is very important for odor control systems, because you want to remove any moisture or water droplets in the airstream before it gets to the adsorbent media, because you don't want to hamper the performance of the adsorbent media itself. So these systems are designed at a particular velocity to ensure proper mist and grease elimination. So you want to have that proper impingement, is what they say, to make sure that filter is going to hold that grease or mist. And these filters are washable and they are reusable. So once they are, say, saturated, they can be removed and cleaned and then replaced. So in most cases for that, the customers will have like a spare to replace it as they clean one, and they just kind of alternate back and forth from there. Here's a kind of a close-up showing you what that filter actually looks like. So you have a 316 mesh followed by fiberglass, then finished off with a more 316 mesh. And the reason why it's designed that way, that I found out about a year ago, is that ensures that the end users or maintenance will not install the filter the wrong way. So you can install it either way, and it's going to work. It's going to perform as intended. So it's a nice foolproof way to make it to ensure that the system's working properly. So dehumidifiers, wanted to kind of touch on this briefly, mainly for plain carbons, because actually the engineered adsorbent medias, they are what you call hygrophilic. So they actually work well in humid environments. For that catalyst, it helps that process to remove the different gases. Well, with plain carbons, you don't want that. You try to avoid having that water molecule present, because actually it will lower the efficiency of the media itself, of the carbon itself. So in some of those applications, you may need some type of dehumidifier, whether it's a duct heater or some type of chill coil, to reduce that humidity before it goes into the actual adsorbent media section itself. It can be very expensive, because these systems will be on the inlet of the units, so quite possibly in the explosive or hazardous envelope, so to speak. So you would need an explosion-proof duct heater as well as any control. So it can be quite expensive and avoided just by using a simple mist and grease filter as described above, and some engineered adsorbents. So just wanted to show that there. Monitoring methods. So you have quite a few different options for monitoring the H2S levels in a system, whether it's the units already installed, or you're in the design process for odor control. So we have manual sampling. So say, for example, the units installed in the previous slide, I showed, units are all equipped with sample ports. So you can use some type of sampling tool, a grain thief type tool, to take core samples of the media and then send back to our lab for testing. It takes a little time for that process, because you take time to sample it, and then take time to ship it, and then wait for the results. So in some cases, to speed that or help that process along, you can use H2S sensors on the inlet and outlet of a unit itself. So different products, for that. We've found some great success using AccuLogs, because as they read to the lower levels, the ppb range, pretty effectively. It also allows the ability to monitor the levels remotely. So that way you have an idea of what H2S levels are coming into the system and what's going out. So you can kind of measure that or track that performance of the system itself. Draeger tubes is another method for sampling or monitoring the different gases, as well as the Jerome analyzer, which is pretty much the gold standard for H2S monitoring, more of a handheld device that's used during performance tests to measure the inlet outlet concentrations when determining system performance. So when it comes to measuring the media itself, as I mentioned, you can take the samples and send it back to PureAir filtration for testing, and we'll give you that report. I'll give you an idea when the media, the remaining media life, or in most cases, at least most of our units, they have we call a media bed monitoring rod. So it's like a dipstick. So that rod is inserted into the first pass of media at a 45-degree angle. So as the media is a rod silver in color, so as the media is being used up, that rod turns black. So it kind of gives the maintenance personnel an idea of when it's time to change out the media. And we actually have taken that technology one step further, and now we have that it's an electronic version of that bed monitor. So now we have a new media bed rod still inserted in the media in the first pass of media at a 45-degree angle, but now this rod has different sensors on the rod itself. So as it reads the H2S, as the breakthrough from the media, it will send a signal back to the control box to give an idea of when it's time to change out the media, or a kind of accurate prediction for the remaining media life. So it's very, very helpful. As the unit's designed, we may design it for 1 year life, running 24/7. Well, what happens if the unit's only running 4 days a week? Well, that media is going to last that much longer. So now we can provide that electronic bed monitor to give you an actual media depletion date. So it's all cloud-based. So that information can be monitored remotely, or even tied into building maintenance, the building maintenance system, or any SCADA. So with either Modbus or 4 to 20 milliamp signal. So very, very beneficial, very helpful for end users. That way, when it's time to change out the media or buy that or replace the media, it can have an accurate prediction versus an issue where there's breakthrough. So system velocities, very important when we're designing systems. Usually if I receive an email or a call from an agent or a rep saying, hey, we have this application where we have, say, 1,000 CFM and 5 ppm of H2S, or whatever the H2S level will be. Typically I'll design the system, if I can, in the budgetary capacity, 50 feet per minute. And I want to ensure that I get the maximum H2S removal throughout the system. So again, as I mentioned, we are concentrating on H2S for this webinar. even though I'm still going to ensure I have a system in place to take out the other odors, but I'm going to size it, based on the H2S concentration. So my first, especially for high H2S concentrations, higher H2S concentrations, I'm going to design at 50 feet per minute. The unit will be a little larger, but if the space is there, it would be, I would say, the safest, the most conservative option. Some cases I'll go up to 75 feet per minute for lower H2S concentrations. Again, we look at it case by case as far as what's the H2S level, how long you want the media to last before change out. Kind of look at those different, I would say, different scenarios when determining what velocities. A lot of we have some competitors that go up to 100 feet per minute on their systems, which we can provide that as well, especially now using the higher capacity engineered adsorbents. We can go with the higher velocities up to 100 feet per minute, but we definitely recommend some on the lower side, 75 feet per minute maximum, if available. Now for the side access housings, for those systems only, we recommend 150 feet per minute. So now we can really reduce the footprint, but as I mentioned previously, that's only for very low odor levels, H2S levels, very low and intermittent. So would not use that, these side access housings for a system that's 5 ppm H2S. You'll be changing out those modules quite frequently, but the very low H2S levels, it can be very cost effective. All right, so empty bed residence time. So in essence, effective odor control is just, and we're just making sure we have that proper contact between the gas and the chemical media itself. So what I just showed here, we have a calculation that we use when determining residence time. Typically, we're using for odor control applications. Typically, the media bed is going to be 3 feet. So from there, based on the velocity, we'll kind of determine, our recommendations for empty bed residence time. So high H2S concentrations, 3.6 seconds, low H2S, 2.4 seconds, and then the very low intermittent H2S levels, cassette systems, 1.2 seconds. And that's just based on the H2S with the velocities that I discussed previously, and using that calculation. All right, the media life calculation, which is important. I wanted to show this calculation is what we used if we know what the airflow, and also the particular gas, in this case H2S, and the H2S level. So we use this this formula to determine the actual media life, and this is based on the unit operating 24 hours a day, 365 days per year, continuous operation. So we will determine the pounds of H2S, and then with that information, we can determine how many pounds of sulfur-absorbed XL would be needed to last at least 1 year. So I did actually a example calculation. So if we had an airflow of 1,000 CFM, H2S concentration level of 20 ppm, so using that formula, we would see about 911 pounds or 413 kilograms of H2S per year. So we know sulfur-absorbed XL has a 66% removal capacity by weight of H2S. So in essence, you would need about 1,400 pounds of sulfur-absorbed XL to last 1 year. If you want to get an idea of the volume, you could just volume required, you just take that pound divided by the density of the media itself. So that way you get an idea. All of our systems are sized via volume, so we can determine what size system will be required to ensure we get the maximum amount of life for H2S, but then we'll also provide a system with a polishing media to remove the remaining odors. And that's, like I said, very important for us, is that we're always going to size a system to make sure we're removing all of the odors. But with H2S being the primary focus. All right, with that, question and answers. Let's see. I see 2 so far. All right, I have a question from Daniel Rodriguez. He said, how is the disposition of the adsorbent material after use? Do we need to manage it as special waste or no? And you do not. It is actually non-hazardous, so it is landfill friendly, as we like to say. So it can be disposed of as normal waste. We just recommend that you follow any local codes when disposing. I know, for example, California, even though the material is non-hazardous, they still have particular landfills that certain waste goes to. So you just have to take a look at it that way. Let's see if there's any other comments. I don't see any. Make sure. Oh, I'm going to chat. No other comments? No questions? No problem. Let's make sure. All right. Well, with that, I would just like to say thank you, everyone, for your time today, and hopefully the information was helpful. If you guys have any questions now or in the future, please feel free to send us an email or give us a call, and we'll be happy to assist in any way possible. I know this presentation will be available, is recorded and will be available shortly. So again, thank you very much for your time. And if you guys have any questions, please feel free to give us a call. Thank you very much. Oh, I have one question from Jaime Escobar. So how do you calculate the pressure vacuum needed for the blower? So we typically, we know the pressure drop, I would say, or the pressure in our media. Typically we request from the end user if they have any external static pressure. If they don't tell us that information, then we will assume whether it's 1 inch of external static pressure. And then from there, we know that, and then we know what our static pressure in our system. So from there, we can size the blower. I hope that was, sorry I didn't see that question. All right, with that, I think I will sign off again.